This video is about everybody's favorite primary pollutant, sulfur dioxide.
Regarding the source of sulfur dioxide emissions, the primary contributor to these emissions are the burning of fossil fuels such as coal, oil, and natural gas by power plants and other industrial facilities. Smaller sources of sulfur dioxide emissions can also include the industrial process of extracting metal from ore and other natural sources such as volcanoes and transportation that burns fuel with a high sulfur content, which can include different transportation means such as locomotives, ships, and heavy equipment. Regarding sulfur dioxide's physical description, its chemical formula SO2 kind of describes it with one sulfur and two oxygen atoms, with covalent bonds existing between the different atoms. It's been known as a colorless gas and has a choking and irritating odor that has been used as a chemical weapon. Sulfur dioxide can be classified as a primary pollutant as it's typically emitted as industrial exhaust from a power plant, factory, or another source. It doesn't react in the atmosphere, which means it can't be classified as a secondary pollutant. There are several negative environmental impacts of sulfur dioxide emissions, which can be traced back to when sulfur dioxide combines with water and air and forms sulfuric acid, which is the prime component of acid rain. There are three separate impacts to acid rain. First is deforestation, which occurs when gaseous sulfur dioxide molecules from acid rain harm trees and plants by damaging foliage and growth. It also weakens trees by damaging their leaves, limiting nutrient uptake, or poisoning them with toxic substances released from the soil. Second, it can damage aquatic waterways by leaching aluminum from clay particles and spilling it over into lakes, marshes, and streams, which kills aquatic life. Third, it can also damage infrastructure by corroding construction materials and paint, and can be economically devastating if it's not taken care of. The Clean Air Act has had a beneficial impact on sulfur dioxide emissions, as when the 1990 amendment to the Act was specifically targeted at reducing sulfur dioxide emissions as a result of acid rain. They implemented a market-based cap-and-trade approach that set a limit on the total amount of sulfur emissions by electric power plants worldwide. One of the ways that this was implemented was the creation of sulfur allowances, which set a limit on the amount of sulfur emissions per power plant in the United States.
Sulfur dioxide has many chemical reactions with many different things. It has a boiling point of -10 degrees Celsius. It's heavier than air, and under prolonged exposure to fire or heat, it violently rockets, and sulfur dioxide interacts with water to create acid rain. And upon exposure to sunlight, wavelengths longer than 290 nm, sulfur dioxide creates sulfur trioxide in the presence of air pollutants, and sulfur dioxide can react with other compounds in the atmosphere and form fine particles that result in haze that reduces visibility, and it is expected to be absorbed in soil when not broken down by microorganisms unless very specific conditions. There are two different measures of which the sulfur dioxide is controlled. The two major emission control methods are sorbent injection and flue gas desulfurization. Sorbent injection involves adding an alkali compound to coal combustion gases for reaction with sulfur dioxide. Typical calcium sorbents include lime and variants of lime, and sodium-based compounds are also used. Sorbent injection process removes 30 to 60% of sulfur oxide emissions. And then flue gas desulfurization may be carried out using either two basic FGD systems, regenerable and throwaway. Both methods may include wet or dry processes, and currently more than 90% of utility FGD systems use a wet throwaway system process.
Sulfur dioxide can be both an indoor and outdoor pollutant. It can be emitted outdoor by the means of factories, volcanoes, and power plants. And it can also be emitted as well indoor through the use of stoves, gas appliances, tobacco smoke, or cigarettes, or chimneys. Regarding the distinction between ground-level ozone and atmospheric ozone, so ozone occurs in two layers of the atmosphere. The layer closest to the Earth's surface is the troposphere. Here, ground-level or bad ozone is an air pollutant that is harmful to breathe, and it damages crops, trees, and other vegetation. It is also the main ingredient of urban smog. The troposphere generally extends to a level about 6 miles up, where it meets the second layer of the stratosphere. The stratosphere, or good ozone, extends upward from about 6 to 30 miles and protects life on Earth from the sun's harmful ultraviolet rays. There are several benefits that the stratospheric ozone layer provides. First, ozone depletion can be caused by increased amounts of UV radiation to reach the Earth, which can lead to more cases of skin cancer, cataracts, and impaired immune systems. Overexposure to UV is believed to be contributing to the increase in melanoma, the most fatal of all skin cancers. Since 1990, the risk of developing melanoma has more than doubled. Radiation can also damage sensitive crops such as soybeans and reduce crop yield. Some scientists suggest that marine phytoplankton, which are the base of the ocean food chain, are already under stress from UV radiation. This stress could have adverse consequences for human food supplies from the oceans.
The formation of the ozone layer can be attributed to when ultraviolet light hits oxygen molecules in the stratosphere. It splits the molecules into two atoms of oxygen. When this atom encounters another oxygen molecule, the two combine to make ozone, or O3. The breaking down of the ozone layer can be attributed to CFC molecules that are made up of chlorine, fluorine, and carbon, or chlorofluorocarbon atoms. They are extremely stable atoms, and this extreme stability allows CFCs to slowly make their way into the stratosphere. This prolonged life in the atmosphere allows them to reach to great altitudes where photons are more energetic. When the CFCs come into contact with these high-energy photons, their individual components are freed from the whole. The following reaction displays how chlorine atoms have an ozone-destroying cycle. Chlorine is able to destroy so much of the ozone because it acts as a catalyst, and chlorine initiates the breakdown of the ozone and combines with freed oxygen to create two oxygen molecules. After each reaction, chlorine begins the destructive cycle again with another ozone molecule. The ozone layer has changed quite a bit due to human activity, but there has been a rapid rise in emissions from the 1960s to the late 1980s, followed by a similarly fast reduction in the decades which followed. In the late 1980s, governments around the world woke up to the destruction of the ozone layer and negotiated the Montreal Protocol, an international treaty to phase out ozone-depleting chemicals. The treaty included a requirement that scientists regularly assess and report on the health of the ozone layer, particularly the annual Antarctic ozone hole. In January of 2011, the Ozone Secretariat of the United Nations Environment Program released its latest reports and noted that the protocol has protected the stratospheric ozone layer from much higher levels of depletion and provided substantial co-benefits by reducing climate change. Emissions had returned to 1960 levels, and this was largely a result of international regulatory agreements and considered action to phase out the production and consumption of these substances. Scientists estimate that if the Montreal Protocol had never been implemented, the ozone hole would have grown by 40% by 2013. Instead, the hole is expected to completely heal by 2050. One of the more overlooked effects of pollution is the effect on varying between developed and developing nations. Developing countries, biomass and coal are usually burned up in open-pit fires that lack the proper mix of fuel and air to allow complete combustion. Usually there's no exhaust system or little or no ventilation in a home, which makes indoor air pollution from carbon monoxide and particulates a particular hazard, whereas in developed countries, homes have become more tightly insulated, which allows existing air to remain in contact with inhabitants for greater amounts of time. This is in part a result of improved insulation, tightly sealed building envelopes, which have been implemented in order to reduce energy consumption. Finally, there are more materials in a home that are made from plastics or other petroleum-based materials that can give off chemical vapors. The first common air pollutant is carbon monoxide. It bonds to hemoglobin, thereby interfering with the oxygen transfer in the bloodstream, causes headaches at low concentrations, and can cause death if prolonged exposure at high concentrations. Another common air pollutant is particulate matter, which can exacerbate respiratory and cardiovascular disease and reduce lung function. It may lead to premature death and also reduces visibility and contributes to haze and smog. The third most common air pollutant are nitrogen oxides. These are respiratory irritants and increase susceptibility to respiratory infection. They're an ozone precursor, which leads to formation of photochemical smog. It converts nitric acid in the atmosphere, which is harmful to aquatic life and some vegetation. It also contributes to over-fertilization of terrestrial and aquatic systems. Fundamentally, sick building syndrome is a buildup of toxic pollutants in an airtight space, such as an office building, that can stem from poor ventilation, typically large office buildings, or chemical contaminants from both the indoors or outdoors. And that does it for our sulfur dioxide video. We hope you enjoyed it, and we hope you stay safe.